Welcome to Lecture, Atomic Structure. Let's begin. It often helps to take a closer look. For example, you might walk up to a sign or a poster in order to make out the details, or you might bring a set of binoculars to a sports stadium so that you can zoom in on the action. The lab technician shown on the next slide is using a magnifying lens to examine a bacterial culture in a petri dish. Scientists use different devices that enhance their ability to see. However, scientists can't always see the details of what they study. In such cases, scientists try to obtain experimental data that helps fill in the picture. Much of the hoopla surrounding the invention of the printing press was that things became very static. You could take a picture, you could make a drawing of a plant, for instance, and pass it around Europe to try to identify it in mass. So this kind of picture really tells 1,000 words, tells a story. Have you ever been asked to believe in something you couldn't see? Using your unaided eyes, you cannot see the tiny fundamental particles that make up matter. Yet all matter is composed of such particles, which we call atoms. An atom is the smallest particle of an element that retains its identity in a chemical reaction. The concept of the atom intrigued a number of early scholars, although these philosophers and scientists could not observe individual atoms. They still were able to propose ideas on the structure of atoms. Here is Aristotle, who used his 5 senses as well as his mind to come up with 4 elements: fire, earth, water, and air that are present in our environment. Between fire and air is hot, between fire and earth is dry, between earth and water is cold, and between water and air is wet. Now, Aristotle certainly was not correct, but if you read on Aristotle, many of our ideas on words and vocabulary come from these early ideas of Aristotle. Aristotle proposed a 5th element, ether, in addition to the 4 proposed by Empedocles. Earth, which is cold and dry. This corresponds to the modern idea of solid. Water, which is cold and wet. This corresponds to the modern idea of liquid. Air, which is hot and wet. This corresponds to the modern idea of gas. Fire, which is hot and dry, this corresponds to the modern idea of plasma and heat. Ether, which is the divine substance that makes up the heavens, the heavenly spheres, and heavenly bodies, stars and planets. Each of the 4 earthly elements has its natural place. All that is earthly tends towards the center of the universe, that is, the center of the earth. Water tends towards a sphere surrounding the center. Air tends towards a sphere surrounding the water sphere. Fire tends towards the lunar sphere in which the moon orbits. When elements are moved out of their natural place, they naturally move back toward it. This is natural motion. Motion requiring no extrinsic cause. So, for example, in water, earthly bodies sink, while air bubbles rise up. In air, rain falls and flame rises. Outside all the other spheres, the heavenly 5th element, manifested in the stars and planets, moves in the perfection of circles. Now we have Democritus, Greek. This is a map of the early atomic model and other timelines. First, we have in the 5th century BC the Greek philosophers, especially Democritus, who coined the term atom from atomos, indivisible, indestructible. We have Sir Isaac Newton. John Dalton is the first scientist to come up with a specific, well-defined atomic theory. We will study Thomson's plum pudding model, Niels Bohr planetary orbits model, and so on. And following this slide are several slides that illustrate the timeline for the development of atomic models. Here are some additional slides to help you understand the timeline for the development of atomic models from 1897 in Thomson to Einstein, to detailed structures of what those models were and how they developed. So it's important to understand the development of the models in order to understand what we have today. Democritus's atomic philosophy. The Greek philosopher Democritus, was among the first to suggest the existence of atoms. Democritus believed that atoms were indivisible and indestructible. Although Democritus's ideas agreed with later scientific theory, they did not explain chemical behavior. They also lacked experimental support because Democritus's approach was not based on the scientific method. This is a picture and sculpture of Democritus, believed that matter of tiny, indivisible, unchangeable particles called atoms. His ideas were later challenged by Greek philosophers Plato and Aristotle. The real nature of atoms and the connection between observable changes in events at the atomic level were not established for more than 2,000 years after Democritus. The modern process of discovery regarding atoms began with John Dalton, an English chemist and schoolteacher. By using experimental methods, Dalton transformed Democritus's ideas on atoms into scientific theory. Dalton studied the ratios in which elements combined in chemical reactions. Based on the results of his experiments, Dalton formulated hypotheses and theories to explain his observations. The result was Dalton's atomic theory, which includes the ideas illustrated in Figure 2. It'll be on the next page. Number one, all elements are composed of tiny, indivisible particles called atoms, similar to Democritus. Atoms of the same element are identical. The atoms of any one element are different from those of any other element. Here's Figure 2. According to Dalton's atomic theory, an element is composed of only one kind of atom, and a compound is composed of particles that are chemical combinations of different kinds of atoms. Now look at A. Atoms of elements are identical. They're the same. B. Atoms of element B are identical, but differ from those of element A. C. Atoms of elements A and B can physically mix together. And then D. Atoms of chemicals A and B can chemically combine to form a compound. So you have atoms of element A and atoms of element B to form compound, which would be called, let's call it AB. Okay, here's a picture of John Dalton, and here are some additional slides illustrating his research into atoms and atomic theory. And we'll talk about some of these later on in this film and also later on in the book. Number 3, atoms of different elements can physically mix together or can chemically combine in simple whole number ratios to form compounds. Number 4, chemical reactions occur when atoms are separated, joined, or rearranged. Atoms of one element, however, are never changed into atoms of another element as a result of a chemical reaction. A coin the size of a penny and composed of pure copper illustrates Dalton's concept of the atom. Imagine grinding the copper coin into fine dust. Each speck in the small pile of shiny red dust would still have the properties of the copper, because those properties, such as density, melting point, etc., are intensive, characteristic physical properties. Now, continuing with the coin analogy, in the second paragraph, it says, if by some means you could continue to make the copper dust particle smaller, you would eventually come upon a particle of copper that could no longer be divided and still have chemical properties of copper. We will see that this is actually an atom of copper. It's an atom of copper. An atom is something that can't be divided and still have the chemical properties of that element. This slide contains evidence that the nucleus, the proton, the neutron, the electron, the atom, they're very, very, very small, in the range from 10 to the negative 10 meters to 10 to the negative 18 meters. Here is a flow chart where you have the atom. It includes electron and the various parts of the rest of the atom, the nucleus, the protons, the neutrons, and connections among things such as hydrogen, periodic table. The size of an electron, for instance, is about 1 over 1840, that of a proton, so it's very small. We would say that it's massless as a result of its size, relatively speaking. The neutron is 1/10,000th of an angstrom, which in itself is very small. So when we look at the atom, we're looking at very small numbers and very large numbers, because when we look at groups of atoms, we're looking at, for instance, what they call a mole, that's 10 to the 23rd. So when we look at atoms, we're looking at very, very large numbers, or very small numbers when we talk about size of an individual atom, etc. This final particle is an atom. We're going back to the copper analogy with the coin being ground up into powder, smaller and smaller and smaller, so that you get an atom. Copper atoms are very small. A pure copper coin the size of a penny contains 2.4 times 10 to the 22nd atoms. By comparison, Earth's population is only about 6 times 10 to the 9th people. There are 4 times 10 to the 12th times, or 4 billion times, 4 trillion times as many atoms in the coin as there are people on Earth. If you could line up 100 million copper atoms side by side, they would produce a line only 1 centimeter long. The radii of most atoms fall within the range of 5 times 10 to the negative 11th to 2 times 10 to the negative 10th meters. Does seeing individual atoms seem possible? Well, it would have seemed possible when I was a kid. It would have seemed impossible when I was a kid. But despite their small size, individual atoms are observable with instruments such as scanning, tunneling microscopes. Figure 3 on the next page shows an image of iron atoms generated by a scanning, tunneling microscope. Individual atoms can even be moved around and arranged in patterns. The ability to move individual atoms holds future promise for the creation of atomic sized electronic devices such as circuits and computer chips. This atomic scale or nanoscale technology could become essential to future applications in medicine, communications, solar energy, and space exploration. Here are some pictures of the results of a scanning tunneling microscope. Scientists used a scanning tunneling microscope to generate this image of iron atoms shown in blue. The radius of this circle of atoms is just 7.13 times 10 to the negative 9 meters. And here is a picture of a scanning tunneling microscope. Variable temperature, ultra high vacuum, atomic force microscope, scanning tunneling microscope. Omicron VTAFMXA. Connecting to your world. A simple but important device, first used by scientists in the late 19th century, the cathode ray tube would achieve its greatest fame as the picture tube of the common television set. Today, cathode ray tubes are found in TVs, computer monitors, and many other devices with electronic displays. But more than 100 years ago, scientists were the only ones staring into the glow of a cathode ray tube. Their observations provided important evidence, very important evidence about the structure of atoms. Many of you have never seen a television set like this. Piecing together atomic structure. It took another 80 years after the Dalton model for scientists to begin gathering clues about the structure of atoms. By 1887, the British scientist William Crookes knew that metal atoms contained negatively charged particles. In a cathode ray tube containing hydrogen gas at low pressure, he found that hydrogen contains positive charges. Scientists knew that the mass of the atom was greater than its proton content. They inferred that this extra mass was due to neutral particles, which were called neutrons. James Chadwick provided evidence for neutrons in 1932. Much of Dalton's atomic theory is accepted today. One important change, however, is that atoms are now known to be divisible. They can be broken down into even smaller, more fundamental particles called subatomic particles. Three kinds of subatomic particles are electrons, protons, and neutrons. Electrons, in 1897, the English physicist J.J. Thomson, 1856 to 1940, discovered the electron. Electrons are negatively charged subatomic particles. Thomson performed experiments that involved passing electric current through gases at low pressure. He sealed the gases in glass tubes fitted at both ends with metal discs called electrodes. And we'll see some examples of that. The electrodes were connected to a source of electricity, as shown in Figure 4. One electrode, the anode, became positively charged. The other electrode, the cathode, became negatively charged. The result was a glowing beam or cathode ray that traveled from the cathode to the anode. In a cathode ray tube, electrons travel as a ray from the cathode negative to the anode positive. A television tube is a specialized type of cathode ray tube. Obviously, we don't use cathode ray tubes anymore in televisions. Here is another example. You have the negative, the positive charge, you have the metal disc, etc. Figure 5a on the next page shows how a cathode ray is deflected by a magnet. A cathode ray is also deflected by electrically charged plates, as shown in Figure 5b on the next page. A positively charged plate attracts the cathode ray, while a negatively charged plate repels it. Here's the Figure 5 that we've been talking about. Thomson examined two ways that a cathode ray can be deflected: by using a magnet, that's an A, by using electrically charged plates. You see them on the left side of the tube, that those two plates are deflecting it. And here's another example of a cathode ray tube and how it's deflected by a magnet. Okay, let's continue. Thomson knew that opposite charges attract and like charges repel, so he hypothesized that a cathode ray is a stream of tiny, negatively charged particles moving at high speed. Thomson called these particles corpuscles. Later they were named electrons. To test his hypothesis, Thomson set up an experiment to measure the ratio of the charge of an electron to its mass. He found this ratio to be constant. In addition, the charge to mass ratio of electrons did not depend on the kind of gas in the cathode ray tube or the type of metal used for the electrodes. Thomson concluded that electrons must be parts of the atoms of all elements. The U.S. physicist Robert Millikan carried out experiments to find the quantity of charge carried by an electron. Using this value and the charge to mass ratio of an electron measured by Thomson, Millikan calculated the mass of the electron. Here is his experiment set up relative to the oil spray and the pinhole and the design, essentially, of the apparatus to help him figure this all out. It was a very unique experiment. Millikan's values for electron charge and mass reported in 1916 are very similar to those accepted today. An electron carries exactly 1 unit of negative charge, and its mass is 1 over 1840, the mass of a hydrogen atom. Protons and neutrons. If cathode rays are electrons given off by atoms, what remains of the atoms that have lost the electrons? For example, this is like 3 days later, sorry about that. After a hydrogen atom, the lightest kind of atom, loses an electron, what is left? You can think, though, this problem using 4 simple ideas about matter and electric charges. First, atoms have no net electric charge. Remember, an atom is a ground state, and the number of protons equal the number of electrons. They are electrically neutral. So, if I ask you, what is the charge of a sodium atom? It's 0. Why is it 0? Because the number of protons equals the number of electrons. The number of protons equal the number of electrons. The number of protons that are in the nucleus, as shown, equal the number of electrons orbiting the nucleus. Here's another example. The protons are in the nucleus. Along with the neutrons, the electrons are orbiting the nucleus. Even though the electrons don't have a large mass, it's negligible, they have a charge that's equal and opposite to the proton. Let's continue. One important piece of evidence for electrically neutral is that you do not receive an electric shock every time you touch something. Second, electric charges are carried by particles of matter. Third, electric charges always exist in whole number multiples of a single basic unit. That is, there are no fractions of charges. Fourth, when a given number of negatively charged particles combines with an equal number of positively charged particles, an electrically neutral particle is formed. Considering all this information, it follows that a particle with 1 unit of positive charge should remain when a typical hydrogen atom loses an electron. Now, if it loses an electron, it has 1 more proton than it does an electron. So its charge will be +1. Its charge will be +1. Here's a cathode ray tube. Evidence for such positively charged particle was found in 1886 when Eugene Goldstein, 1850 to 1930, observed a cathode ray tube and found rays traveling in the direction opposite to that of cathode rays. He called these rays canal rays and concluded that they were composed of positive particles. Such positively charged subatomic particles are called protons. Each proton has a mass about 1,840 times that of an electron. In 1932, the English physicist James Chadwick confirmed the existence of yet another subatomic particle, the neutron. Neutrons are subatomic particles with no charge, but with a mass nearly equal to that of a proton. On the next page, Table 1, summarizes the properties of these subatomic particles. Although protons and neutrons are exceedingly small, theoretical physicists believe that they are composed of yet smaller subnuclear particles called quarks. Here is a table which lists the 3 main subatomic particles that we will study. All of this is familiar to you. Look at the electron. It is 1,1840, 1 over 1,840, that of a proton. So we say that its mass is negligible, but it does have a mass as listed there. Here is a diagram for the Bohr model, and here are the other models: the Dalton model, the Thomson model, Rutherford, Bohr, and the Schrödinger electron cloud of 1926. Notice the dates, 1803, and then it was not for another 100 years that you had a viable model that we will study called the Thomson plum pudding model. And then you had 3 successive ones. In 1926 is very similar to what we think of it as today. Here is an electron cloud model, and you can see that it is very similar to some of the other models relative to charges and a strong nucleus. The atomic nucleus. When subatomic particles were discovered, scientists wondered how these particles were put together in an atom. This was a difficult question to answer, given how tiny atoms are. Most scientists, including J.J. Thomson, the discoverer of the electron, thought it likely that these electrons were evenly distributed throughout an atom filled uniformly with positively charged material. Now, this was called the plum pudding model. And we will look at the plum pudding model as a significant advancement in the understanding of atomic structure. In Thomson's atomic model, known as plum pudding model, electrons were stuck in a lump of positive charge, similar to raisins stuck in dough. This model of the atom turned out to be short-lived. However, due to groundbreaking work of Ernest Rutherford, a former student of Thomson. So this was the Thomson model was short-lived, as were some of the other models, including the Rutherford model, because of the accelerated advancement of our understanding of the atomic structure in the early 20th century. Let me read part of that again. It says, this model of the atom, the plum pudding model, turned out to be short-lived, however, due to the groundbreaking work of Ernest Rutherford. Next page, figure 6. This was Ernest Rutherford. That is on the $100 note of the country of New Zealand. Ernest Rutherford, try to say that 10 times fast, was the scientist who performed the famous gold foil experiment, and we'll talk about that in great detail. Here are some pictures, the next 5 slides, including this one, which details some of the results of the gold foil experiment, and I'll talk while the movie is playing. In the gold foil experiment, you had alpha particles which were shot at gold foil, and most of the alpha particles went directly through the gold foil, but some of the alpha particles were deflected. This was the discovery of the nucleus, and it was a tremendous discovery. And it was not only the discovery of the nucleus that was significant, but the size of the nucleus was small, but yet the density of it, and the power of the nucleus relative to deflecting these alpha particles that relative to momentum were moving very fast, and to be deflected demonstrated that they were hitting a gigantic mass that we now know to be called the nucleus. And we'll study this in great detail. Some of the slides that we'll look at detail the gold foil experiment relative to the percentage of alpha particles that were deflected less than 5 degrees from the target. And most of the particles, the vast majority of particles, were actually deflected very little. But those that were not deflected very little gave evidence that there must have been a massive structure in their way. Rutherford's gold foil experiment in 1911, Rutherford and his co-workers at the University of Manchester, England, decided to test what was then the current theory of atomic structure. Their test used relatively massive alpha particles, which are helium atoms that have lost their 2 electrons and have a double positive charge because of the 2 remaining protons. So it has a mass of 4. It has 2 neutrons and 2 protons, and it has a charge of 2. In the experiment illustrated in figure 7 on the next page, a narrow beam of alpha particles was directed at a very thin sheet of gold foil. According to the prevailing theory, the alpha particles should have passed easily through the gold, with only a slight deflection due to the positive charge thought to be spread out in the gold atom. So part of that was a result of the Thomson model, the plum pudding. That's where that whole idea came from. Figure 7, it will continue on the next page. Rutherford's gold foil experiment yielded evidence of the atomic nucleus. A. Rutherford and his co-workers aimed a beam of alpha particles at a sheet of gold foil surrounded by a fluorescent screen. Most of the particles passed through the foil with no deflection at all. A few particles were greatly deflected. Rutherford concluded that most of the alpha particles passed through the gold foil because the atom is mostly empty space. The mass and positive charge are concentrated in a small region of the atom. Rutherford called this region the nucleus. Particles that approach the nucleus closely are greatly deflected, and this was evidenced by the calculations of the momentum of the alpha particles and what must have been present to change the momentum of these individual alpha particles. And here is a shot of the screen right from the book, and it shows you that most of the particles will pass right through because of the large nature of the gold atom. And as we've learned even to this point, that most of the atom is empty space. These electrons, these massless electrons jumping around, creating this cloud. So it's difficult to study. It's difficult to study atomic structure in a vacuum because so much of what we study in chemistry and atomic structure is influenced by the entire history of atomic structure and the current knowledge of quantum mechanics and the electron cloud that we know exists. To everyone's surprise, the great majority of alpha particles passed straight through the gold atoms without deflection. Even more surprisingly, a small fraction of the alpha particles bounced off the gold foil at very large angles, as said in the figure. Some even bounced straight back towards the source. Rutherford later recollected, "This is almost as incredible as if you fired a 15-inch shell, that's more than a foot long, a third of a meter. In terms of the size of the shell, it's an artillery shell." So it says, this is almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you because of the momentum differences. The Rutherford atomic model, based on his experimental results, Rutherford suggested a new theory of the atom. He proposed that the atom is mostly empty space, thus explaining the lack of deflection of most of the alpha particles. As we know, that's actually quite true. He concluded that all the positive charge and almost all of the mass are concentrated in a small region that has enough positive charge to account for the great deflection of some of the alpha particles. He called this region the nucleus. The nucleus is the tiny central core of the atom and is composed of protons and neutrons. Rutherford's atomic model is known as the nuclear atom. In the nuclear atom, the protons and neutrons are located in the nucleus. The electrons are distributed around the nucleus and occupy almost all the volume of the atom. According to this model, the nucleus is tiny compared with the atom as a whole. If an atom were the size of a football stadium, the nucleus would be about the size of a marble. Although it was an improvement over Thomson's model of the atom, Rutherford's model turned out to be incomplete and short-lived as well. In Chapter 5, you will learn how Rutherford's atomic model had to be revised in order to explain the chemical properties of elements. Connecting to your world. Fruits and vegetables come in different varieties. For example, a grocery store might sell 3 varieties of apples: Granny Smith, Red Delicious, and Golden Delicious. Apple varieties can differ in size, color, size, texture, aroma, and taste. Just as apples come in different varieties, a chemical element can come in different varieties called isotopes. In this section, you will learn how one isotope of an element differs from another. An isotope is a variation of an element based on the number of neutrons. The 3 isotopes will have the same number of protons because it's the same element but different number of neutrons and different mass. Atomic number. Atoms are composed of protons, neutrons, and electrons. Protons and neutrons make up the nucleus. Electrons surround the nucleus. How then are atoms of hydrogen, for example, different from atoms of oxygen? Look at Table 2 on the next page. Notice that a hydrogen atom has 1 proton, but an oxygen atom has 8 protons. Elements are different because they contain different number of protons. The atomic number of an element is the number of protons in the nucleus, and an atom of that element. Because all hydrogen atoms have one proton, the atomic number of hydrogen is 1. Here are the first 10 elements: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And you can see that they're listed from 1 to 10, and the atomic number equals the number of protons. If they're atoms, the number of electrons equals the number of protons. The number of neutrons plus the number of protons will equal the mass number, or the number of nucleons in the nucleus. Similarly, because all oxygen atoms have 8 protons, the atomic number of oxygen is 8. The atomic number identifies an element. For each element listed in Table 2, the number of protons equals the number of electrons. Remember that atoms are electrically neutral, ground state. Thus, the number of electrons, negatively charged particles, must equal the number of protons, positively charged. You know that most of the mass of an atom is concentrated in the nucleus and depends on the number of protons and neutrons. The total number of protons and neutrons is called the mass number. Look again at Table 2. Go back and note the mass numbers of helium and carbon. A helium atom has 2 protons and 2 neutrons, so its mass number would therefore be 4. A carbon atom, which has 6 protons and 6 neutrons, has a mass number of 12. If you know the atomic number and mass number of an atom of any element, you can determine the atom's composition. Table 2 shows that an oxygen atom has an atomic number of 8 and a mass number of 16. If you write the standard form of an element, the symbol, you have the mass number in the superscript and the atomic number in the subscript. Because the atomic number equals the number of protons, which equals the number of electrons, an oxygen atom has 8 protons and 8 electrons. The mass number of oxygen is equal to the number of protons plus the number of neutrons. The oxygen atom then has 8 neutrons, which is the difference between the mass number and the atomic number. 16 minus 8 equals 8. 16 minus 8 equals 8. The number of neutrons in an atom is the difference between the mass number and the atomic number. Number of neutrons equals mass number minus atomic number. The composition of any atom can be represented in shorthand notation using atomic number and mass number. Figure 8 on the next page shows how an atom of gold is represented using this notation. The chemical symbol Au appears with 2 numbers written to its left. The atomic number is the subscript, the mass number the superscript. You can also refer to atoms by using the mass number, and the name of the element. For example, 197 over 79 Au may be written as gold hyphen 197, 197 being the mass number. It says figure 8, Au is the chemical symbol for gold. Now let's apply concepts. How many electrons does a gold atom have? It says atom, so the number of protons and electrons would be equal. So look up the atomic number, which is 79, so it would have 79 electrons. Going clockwise from the upper left, those are gold bars of pure gold, and we have a nugget of gold. We have some more gold bars. We have a gold mine, and probably somewhere in South America is bottom central, continuing an old drawing of some sort of possibly mining gold in the Old West. Gold is a much sought after element. No news to anybody in the class. Gold makes a great gift. It's worth a lot of money because of reasons of chemistry. It's chemistry which makes gold so expensive. Figure 9 on the next page shows that there are 3 different kinds of neon atoms. How do these atoms differ? All have the same number of protons, 10, and electrons 10, but they each have different numbers of neutrons. Isotopes are atoms that have the same number of protons, but different numbers of neutrons. That's the definition. An isotope, two isotopes are of the same element. They're just variations of the same element based on the number of neutrons. So here's figure 9, neon 20, neon 21, neon 22, and there's the data for each. You see that the only difference among the three is the number of neutrons, 10, 11, 12, neon 20, 21, and 22 respectively. Neon is used as a gas, it's an inert gas, and it shows up red in terms of rock and roll, those portions of the sign that to the right. Because isotopes of an element have different numbers of neutrons, they also have different mass numbers. Despite these differences, isotopes are chemically alike because they have identical numbers of protons and electrons, which are the subatomic particles responsible for chemical behavior. Here is lithium 6, 7, and 8. All are lithium because they have 3 protons, however, different numbers of neutrons, 6, 7, 8, respectively. For each one would have 3, 4, 5, respectively. These are 3 known isotopes of hydrogen. Each isotope of hydrogen has 1 proton in its nucleus. The most common hydrogen isotope has no neutrons. It has a mass number of 1 and is called hydrogen 1, or protium, or simply hydrogen. The second isotope has 1 neutron and a mass number of 2. It is called either hydrogen 2 or deuterium. The third isotope has 2 neutrons and a mass number of 3. This isotope is called hydrogen 3 or tritium. Here is protium, deuterium, and tritium. Here are examples of them, and here you also have 2 examples of helium-3 and helium-4. So not only do you have protium, deuterium, and tritium, you also have helium-3 and helium-4. Note the way you say it. You say the name of the element, hyphen, and then the mass number. So helium-3, helium-4. Helium-3 has 1 neutron, helium-4 has 2. And hydrogen 1, 2, and 3, or protium, deuterium, and tritium. Here you have 1 electron in each, so that's no big deal. You also have 1 proton in each. However, the difference is 0 neutrons for hydrogen 1, 1 neutron for hydrogen 2, and 2 neutrons for hydrogen 3, giving the mass numbers 1, 2, and 3, respectively, for protium, deuterium, and tritium. Here is iodine. You have iodine 131 and iodine 127, same number of protons. However, the number of neutrons are significantly different. I would say 4 neutrons is pretty different relative to masses. However, remember also that the number of protons are the same and the number of electrons are the same, so the chemistry is the same, just different masses. Nuclei and relative abundance of carbon isotopes. Here we have carbon isotopes where carbon 12 is 98.9%, carbon 13 is 1.1%, and carbon 14 used in the dating of fossils is less than 0.0001%. And the protons are green and the neutrons are purple. Here again is another view of isotopes that we have seen: hydrogen 1, 2, and 3, protium, deuterium, and tritium, helium 3 and 4, and lithium 6 and 7. Even though you have lithium 8, the vast majority of lithium is composed of both lithium 6 and 7, and red being proton and green being neutron or neutral. Atomic mass. A glance at table 1 on page 106 shows that the actual mass of a proton or neutron is very small, 1.67 times 10 to the negative 24 grams. The mass of an electron is 9.11 times 10 to the negative 28 grams, which is negligible in comparison. Given these values, the mass of even the largest atom is incredibly small. Since the 1920s, it has been possible to determine these tiny masses by using a mass spectrometer. With this instrument, the mass of fluorine atom was found to be 3.155 times 10 to the, let's change the timing, 3.155 times 10 to the negative 23 grams, and the mass of arsenic atom was found to be 1.244 times 10 to the negative 22 grams. Such data about the actual masses of individual atoms can provide useful information, but in general, these values are inconveniently small and impractical to work with. Instead, it is more useful to compare the relative masses of atoms using a reference isotope as a standard. The isotope chosen is carbon-12. C, capital C, to the left, 12 over 6. Carbon-12 is the isotope chosen as the standard. This isotope of carbon was assigned a mass of exactly 12 atomic mass units. An atomic mass unit, AMU, is defined as 1/12 of the mass of carbon-12 atom. Using these units, a helium-4 atom with a mass of 4.0026 AMU has about 1/3 the mass of carbon-12 atom. On the other hand, a nickel-60 atom has about 5 times the mass of the carbon-12 atom. So carbon-12 is the isotope that was chosen to use as a standard when measuring the relative masses of atoms from the periodic table. A carbon-12 atom has 6 protons and 6 neutrons in its nucleus, and its mass is set at 12 AMU. The 6 protons and 6 neutrons account for nearly all of this mass. Therefore, the mass of a single proton or single neutron is about 1/12 of 12 AMU or 1 AMU. Because the mass of any single atom depends mainly on the number of protons and neutrons in the nucleus of the atom, you might predict that the atomic mass of an element should be a whole number. However, that is not usually the case. The plot is thickening. That's a very, very important aspect of finding out what these masses mean. In nature, most elements occur as a mixture of 2 or more isotopes. Each isotope of an element has a fixed mass of a natural percent abundance. Consider the 3 isotopes of hydrogen discussed earlier in this section. According to Table 3, on the next page, almost all naturally occurring hydrogen, 99.985%, is hydrogen 1. The other 2 isotopes are present in trace amounts. Notice that the atomic mass of hydrogen listed in Table 3 is 1.0078 AMU, is very close to the mass of hydrogen 1, 1.0078 AMU. The slight difference takes into account the larger masses but smaller amounts of the other 2 isotopes of hydrogen. Now, consider the 2 stable isotopes of chlorine listed in Table 4.3, chlorine 35 and chlorine 37. If you calculate the arithmetic mean of these 2 masses, 34.969 AMUs and 36.966 AMUs divided by 2, you get an average atomic mass of 35.968 AMU. However, this value is higher than the actual 35.453. To explain this difference, you need to know the natural percent abundance of the isotope of chlorine. Chlorine 35 accounts for 75% of the naturally occurring chlorine atoms. Chlorine 37 accounts for only 25%. See Figure 10. The atomic mass of an element is a weighted average mass of the atoms in a naturally occurring sample of the element relative to isotopic abundances, and the average mass of all the atoms in the sample. A weighted average mass reflects both the mass and the relative abundance of the isotopes as they occur in nature. I think I just said that. Now that you know that the atomic mass of an element is the weighted average of the masses of the isotopes, you can determine atomic mass based on relative abundance. To do this, you must know three values: the number of stable isotopes of the element, the mass of each isotope, and the natural percent abundance of each isotope. To calculate the atomic mass of an element, multiply the mass of each isotope by its natural abundance, expressed as a decimal, and then add the products. The resulting sum is the weighted average mass of the atoms of the element as they occur in nature. You can calculate the atomic masses listed in Table 3 based on the given masses and natural abundances of the isotopes for each element. For example, carbon has two stable isotopes: carbon-12, which has a natural abundance of 98.89%, carbon-13, which has a natural abundance of 1.11%. The mass of carbon-12 is 12 AMUs. The mass of carbon-13 is 13.003 AMU. The atomic mass is calculated as follows. And atomic mass of carbon is going to be 12 times 0.9889 plus 13.003 times 0.0111. You're going to add all that up and then divide by 100, and you're going to get 12.011 AMU. You really should be using the carbon-14 in terms of the calculation, but for whatever reason the book is ignoring that fact. Here is a periodic table. I guess they just wanted to show you a periodic table. Now that you can differentiate between atoms of different elements and also between isotopes of the same element, you need to understand how the elements are organized with respect to each other. A periodic table, which we just saw, is an arrangement of elements in which the elements are separated into groups based on the set of repeating properties. A periodic table allows you to easily compare the properties of one element or group of elements to another element or group of elements, such as in figure 11 on the next page. Shows the most commonly used form of the periodic table, sometimes called the long form. This is the periodic table long form. And this is, I've never heard it called the long form, but anyway, that is the periodic table. Each element is identified by its symbol placed in a square. The atomic number of the elements is shown centered above the symbol. Notice that the elements are listed in order of increasing atomic number, to the left, to the right, and top to bottom. Hydrogen H, the lightest element, is at the top left corner. Helium, atomic number 2, is at the top right. Lithium, Li, atomic number 3, is at the left end of the second row. Each horizontal row of the periodic table is called a period. There are 7 periods in the modern periodic table. There are 7 periods in the modern periodic table. Let me say that once more. There are 7 periods in the modern periodic table. The number of elements per period ranges from 2 in the first period, hydrogen and helium in period 1, to 32 in period 6. Within a given period, the properties of the elements vary as you move across it from element to element. This pattern of properties then repeats as you move to the next period. Each vertical column of the periodic table is called a group or family. Elements within a group have similar chemical and physical properties. Note that each group is identified by a number and a letter A or B. For example, group 2A contains the elements beryllium, Be, magnesium Mg, calcium Ca, strontium Sr, barium Ba, and radium Ra. You will learn more about specific trends in the periodic table in Chapter 6. I will also put the periodic table in again between this slide and the next so that you can peruse it based on what we just talked about. And I'll put it on for a good 60 seconds or so to give you a chance to examine it based on the text that I am reading from. So here is the periodic table. I will let you peruse it and maybe read over or listen to again the text that I read from the last couple of slides. I'll be back after the slide is finished. Notice these are numbered the American style, 1A, 2A, and then over on the right 3A, 4A, 5A, etc. As to what the IPAC, they number it 1 through 18, and we use both. We use 1A, 2A. I mainly use 1 through 18. I feel that that's generally the best. It would be nice to know and to do what the rest of the world agrees upon as a chemistry teacher. Okay, archaeologists are detectives of the past, sifting for clues that uncover secrets of past civilizations. Archaeologists excavate ancient cities and dwellings looking for artifacts that indicate what kinds of food ancient people ate, what types of tools they used, and how they interact with one another as a society. Often archaeologists must draw conclusions based on indirect evidence, knowing when an event occurred or when an artifact was made can provide important information. One of our first experiments was indirect versus direct measurement. Now we're going to look at archaeology as a way of measuring directly and indirectly. Archaeologists use techniques such as radiometric dating, in which a sample is dated by measuring the concentration of certain isotopes such as carbon-14. This method tells them the age of a sample within a certain range and is used with the greatest accuracy for samples no more than 10,000 years old. Archaeologists also perform chemical tests on artifacts to determine what composition. For example, archaeologists might analyze the glazes used on pottery or the dyes used in clothing. Remember, all material is made of chemicals and subject to study here. Archaeologists may also use chemicals to preserve artifacts that have been unearthed so that the artifacts can be examined without being damaged. Archaeology requires a background to both history and science. Archaeologists often spend as much time in the laboratory studying their finds as they do out where, to be continued. But this is Indiana Jones stuff, and this is not just a burial pit. This is an archaeological dig. Looks pretty recent though, but more on that later. New dinosaur species, fossil discovered in northwest China. This is just an example of how we study archaeology. A team of international scientists has unearthed the fossil of a new species of pterosaur and its eggs, according to the Chinese Academy of Sciences on Friday. The fossils were discovered in the city of Hami in northwest China's Xinjiang Uyghur Autonomous Region and date back to the early Cretaceous period, said Wang Ziolin, a researcher at the CAS who is in charge of that particular excavation. The pterosaurs are sexually dimorphic, and 5 of their eggs are 3-dimensionally preserved, marking a first worldwide marking a first worldwide. Before their discovery, there had only been 4 flattened, two-dimensional preserved pterosaur eggs. The team has named the new species Hamitotaurus or something after the place they were found. Most of the fossils are relatively intact, and this is favorable for assembly of a complete pterosaur skeleton, Wang said. Pterosaurs were enormous creatures, and the next slide will show the relative size of a pterosaur relative to humans and giraffes. This is a pterosaur. Must have had awfully small bones to be so large and to be able to fly so well, according to the way we interpret the skeleton of the pterosaur. So pterosaurs are pretty scary things. I'll just let this slide run and you can examine the pterosaur. So if a man or woman, 6 foot or less, something like that, look at where the pterosaur's knee is. So we're knee high to a pterosaur. It's pretty amazing. And then the wingspan would be incredible as well. So the pterosaur altogether would have been terrifying to see overhead. Look at that beak, like a giant spear. These fossils will shed new light on the reproduction, development, and behavior of pterosaurs, according to Wang. The new findings were published in the international core journal Current Biology in cooperation with Brazilian paleontologist Alexander Kellner and other scientists on Thursday. So something to look up. Remember, anything we study really is chemical. So all matter, anything, all material is fair game for the study of chemistry. Hope you enjoyed it. Test coming up, and good luck.